Hello, hello, citizens of Planet Math. I just made that up. We're starting 4.2 vector spaces. So in 4.1, we talked about vectors, and I just want to give you I guess what I want to say is 4.1 was more concrete, more like the kind of vectors we represented vectors the way you used to doing it with arrows and stuff like that. And in 4.2, it's going to get a little bit more abstract, but trust me, it's going to be worth it. Um, and we're going to define something called a vector space. Now, we listed, if you remember, way back in 4.1, we listed these 10 properties. See, here they are. Whoops, right there. We had these 10 properties that you find in Rn, and we showed that these properties work in Rn. Well, we're going to now define something called a vector space. What we're going to say is that any set which has these 10 properties work is going to be called a vector space. And that's really the starting point for 4.2. And I just want to note one thing. This is kind of see here it says we're axioms. See, when we did back before, we called them theorems. There were 10 theorems about Rn. Now we'll call them axioms, because what we mean to say is like this. When it came to the R2 and Rn and all those other things, we had to prove that these properties worked. But what we're saying now, the definition of a vector space, I'm going to bring it up right here. The definition of a vector space is that any set where these properties work, any set that has these properties is going to be called a vector space. So these properties are called the axioms of a vector space. Now, you may have to prove an axiom is something that you don't prove. An axiom is not something that you prove, it's something that's a sort of a given, it's a foundationary principle. So we back in 4.1, we proved that Rn has these 10 properties. So we proved that Rn qualifies to be called a vector space. And that's the difference. That's the difference in that's why the word axiom. But basically, we're seeing from this definition here that as long a vector space consists of 4 entities, it has to be a set of vectors. So it's a set of things which we're calling vectors. It has to have a set of scalars, and it has to have 2 operations. Vector addition and scalar multiplication. And so, of course, R2, we already showed that R2, the standard operations, is a vector space. Now, you notice it says here the word standard operation. This might make you think, is there such a thing as R2 with a non-standard operation? And yes, indeed there is. Indeed, there is such a thing. And we'll get to that. But I'm just giving you a little foreshadowing here. Moving on. Rn with the, oh boy. Rn with the standard operations is a vector space, and we'd already showed this. That was what that theorem 4.2 was all about. We showed this already. By the way, R1 would also be a vector space if we want to view it that way. Well, let's look at a new vector space. Let's look at something else, some other examples of sets which have the vector space properties. So one example would be the set of all 2x3 matrices. The set of all 2x3 matrices, this is going to form a vector space. Why is that? Well, very simple. Let's just go through it. Let's go through it bit by bit. If you add a 2x3 matrix to another 2x3 matrix, you get a 2x3 matrix. So this closure. If you multiply a 2x3 matrix by a scalar, you get a 2x3 matrix. So again, that's a scale. So we have closure. Those are 2 important properties. And so it's closed. That's what we're trying to say. It's closed. And further, all the other things just work because we know that matrices, we've already shown a long time ago that matrices are commutative, and addition of matrices is commutative, and it's associative, and there's an identity element and a zero matrix, and so on and so forth. So the set of all 2 by 3 matrices is quote a vector space where each matrix is called a 2 by 3 matrix. This guy down here, this does not look anything. This does not look anything like an arrow, but like I say, it doesn't have to be. That's not the point. It doesn't have to be the sort of arrows that we've always seen in the past. By the way, I just want to note that 2 by 3 is matrices. That's just an example. We could have looked at the vector space of all 5 by 7 matrices, or all 8.5 by 11 matrices. Oh wait, how can I have 8.5? Oh, I'm thinking of paper size. 8 by 11 matrices, or 52 by 19 matrices. Any of these would work. Now let's look at another type. Again, this is very, very different. Now we're going to go to another example of something very, very different. The vector space of all polynomials of degree 2 or less. So degree 2, that would be, ax squared bx plus c. But we're not going to, instead of saying ax squared plus bx plus c, we're very cool here, and we say a2 x squared plus a1 x plus a naught. And we're looking at all the vector space of all the polynomials of degree 2 or less. So let's just look at this. If P1 is a2 x squared plus a1 x plus a naught, and Q of x is another such polynomial, which is b2 x squared plus b1 x plus b naught. Well, if I add P of x plus Q of x, I get a2 plus b2 x squared, a1 plus b1 x, a naught plus b naught. So basically, this I have this fits the definition of ax squared bx squared plus bx plus c. That's my you get my point. So it all fits. So we have closure. Further, if I take p of x and multiply it by some scalar c, I just get. So now the coefficients, instead of the coefficient being a2, now the coefficient is ca2, and the coefficient here is ca1, and the coefficient here is ca0. So we have closure. Well, everything else is going to be pretty simple, because it's dealing with numbers. Now here we're going to show here we're going to show the what's the word I'm looking for? Commutative property. So P of x plus Q of x. So it's a2x squared a1x plus a naught plus b2x squared b1x b naught. I can sort of factor and rearrange everything. This is going to be equal to a2 plus b2 x squared, a1 plus b1x, a naught plus b naught. Now I can switch the a's and b's, because these are just plain numbers. So I know that plain numbers are commutative, and now that I've done this, I can redistribute and group everything together. And I have b2x squared, b1x, b naught, a2, a1, a naught, which is really my q of x plus my p of x. So I went through a whole long process here to show that p plus q is equal to q plus p. And there's going to be a zero vector, because 0 of x, I'm going to call that 0x squared plus 0x plus 0. And all the other properties are not that hard to show. Associativity, they're going to follow pretty easily. And I'll let you, but I want you to verify that on your own. Let's go to another example. Okay, look at this. Now, again, we're looking at the set of all continuous functions. So this is something that we know from calculus. We have the concept of a continuous function. And we know that continuous functions, we know that when you add two continuous functions, the result, you get a continuous function. Again, it's something we know from calculus. And we know that if you multiply a continuous function by a scalar, the result is going to be a continuous function. So we see that the set of continuous functions, this means a set of continuous functions that are defined on all real numbers. So and this is a set of all real, otherwise known as a set of all real valued continuous functions, uh, defined on the entire real line. So uh, this, so we know that these are so f like sine x plus e to the x. We know it's closed, and it's again very easy to verify that all the other conditions work. Um, for if I here's my zero function, it's a function which is which is a constant function which just equals zero, and here's a here you see that if I add two function, if I add the zero function onto another function x, I get f of x plus f naught of x, which that's just by definition, which is f of x plus zero, which is plain f of x. So the zero function does serve as the identity element of addition. Uh, Adding functions is commutative and it's associative and all these other things. It's again, it's very easy to show, and I'll leave it up to you to fill in all 10. But again, this is a really great example because these things don't look like little arrows; they're curvy function thingies. So that's really what I'm trying to show you. Now, I want to give you a little list here of very famous and important vector spaces. So of course, the set of real numbers, R2, R3, may as well just go straight to Rn. The set of all continuous functions that are defined on the entire real number line. This one here, C of AB, that means the set of all continuous functions defined on a specific closed intervals. P is a set of all polynomials. I want to get back to that one. Pn is what we did before, like set of all polynomials of degree less than or equal to n. We did an example when n equal 2, and m the set of all m by n matrices, or the set of all n by n matrices, square matrices. I want to point out some of this. The set of all oops. Okay, well, that's not what I wanted. Let me get rid of this. This one here, the set of all polynomials. We didn't really discuss this one. You see, here we're talking about polynomials. We did Pn, polynomials of degree 2 or less. But set of all polynomials, that means a set of all polynomials of any degree. And it includes all these second degree, third degree, fourth degree, fifth degree, ad infinitum. So if I add any two polynomials, the result is a polynomial. If I multiply a polynomial by a scalar, again, the proof of this is pretty, straightforward. That's all I wanted to say. Moving on. This is a very straightforward properties of scalar multiplication. If I multiply any of these vectors by 0, I get the 0 vector. If CV equals 0, then it's either C equals 0 or V equals 0, so on and so forth. Let's just take a look over here. And to prove these, so let's just give an example of some proofs. So to prove the C times the 0 vector, now the 0 vector is equal to 0 plus 0. So C times the 0 vector is C times 0 plus 0, which is C0 plus C0. And now I add the inverse, and I get, which winds up giving me that 0 is equal to C0 plus 0, but C0 plus 0 is equal to C0. So basically this whole long proof was to show me that C times the 0 vector is equal to the 0 vector. And I know it seems like very long and arduous to prove something that's pretty obvious, but we're working just based on the axioms that we had, not assuming anything else. And this one is similar. We want to if C times the vector is equal to 0, we want to show that this implies either C equals 0 or V equals 0, because if C was not equal to 0, right? If C was not equal, well, C is equal to 0, then there's nothing to prove. But if C does not equal 0, then then C has a reciprocal 1 over C, and to show that V is equal to 0, V is equal to 1 times V. That's one of the axioms. and that's equal to 1 over C times V, which is 1 over C times CV. But CV we know is 0, so it's 1 over C times 0, which is 0. So we've shown in this whole long steps here that vector V is equal to 0. Okay, lovely. And we can go through all the proofs. I'll let you do that as next time, but you should definitely do that. This is something you may remember about springs and a very interesting application. And this does form a vector space. Now, let's look at some examples where they're not vectors. Okay, so the set of integers is not a vector. Why is that? Because if you multiply it by a scalar, then the result is not an integer. So 1 is an integer. If I multiply it by the scalar 1/2, the result is 1/2, but 1/2 is not an integer. So you see, the set of integers is not closed under scalar multiplication. Now, what about the other 9 axioms? There are 10 axioms. Well, as long as you show that one axiom doesn't work, that means it's not a vector space, which is what I always say. It's much easier to disprove something than to prove something. You see, if I want to prove that something is a vector space, I have to go establish all 10 axioms. If I want to disprove something from being a vector space, then I just have to find one that doesn't work, and we're done, and that's it. We're good. So in general, disproving something is actually easier than proving something. Okay, now when we had the going back to a previous example, we were going back to, oh, here we go, just passed it. In this example here, we had the words or less, and I didn't really make a big thing out of that. I kind of glossed over it, but the words or less, we never really made a big point of what that meant, and but those words are actually critically important for why this is a vector space. And the following example, which I'm about to show you, is not going to be a vector space. So let's say we have the set of all second degree polynomials, not second or less, but strictly second degree polynomials. That's not going to be a vector space. I'll show you why. Suppose I take P of X is equal to X squared, and Q of X is equal to negative X squared plus X plus 1. Well, when I add P plus Q, the positive X squared and the negative X squared are gonna cancel. See, there's, oops, one minute. Let me try to be fancy. The positive X squared and the negative X squared, these guys are gonna cancel out, and I'm gonna get X plus 1. Well, X plus 1 is not a second degree polynomial, it's a first degree polynomial. So in the example I gave earlier that was a good vector space, that's why I had to include second degree or less. Because if you include X plus 1, if you include first degrees as part of your space, then it's going to be closed, or 0 degrees. Because what if P of X was X squared minus 1, and then the minus, or X squared minus X, which would cancel out with that, in other words, I could, I have to do second or less. Wait, I just want to be clear on what I was just saying. Suppose P of X was X squared minus X, then the minus X would cancel out that plus X, and I would just get P plus Q equals 1. So I have to include 0 degree polynomials, if you will, in my system. So, by the way, I call it a 0 degree polynomial. Some people do call it a 0 degree polynomial. Some people don't call it a 0 degree polynomial, but whatever. You understand what I mean. I knew what I meant. You knew what I meant. Let's move on. Number 8, another set which is not a vector space. Now, this is super duper important. Example 8. In example 8, Now, the previous examples failed because they weren't closed. This one is closed under, um, but I want to make a bunch of points here. Here's a set which is not a vector space. So V is equal to the set of R2, which is ordered pairs of real numbers. And it has a standard operation for addition, and it has a non-standard definition of scalar multiplication, where C times X, now X1 comma X2, the same thing as X comma Y, is equal to CX1 and comma 0. Now, this is a different definition of scalar multiplication. So, and that's my point. That's the point we tried to make earlier, meaning that when you talk about a vector space, you're not just talking about the set. I'm not just talking about R2. I'm not just talking about the set of ordered pairs of real numbers, but I have to, a vector space is not just the set itself, but it's the operations on the set, or how you define the operations on the set. And since I'm defining scalar multiplication in a different way, that makes it a different vector space. So this is not the vector space R2, the standard vector space R2 that we know and love. It's R2, it's the same vectors, it's the same set, but it's a different operation. So that's gonna make this, and that's gonna wind up making this not a vector at all. And this is kind of interesting because, so for example, if I have 3 comma 4 and I multiply that by the scalar 2, that's 3 times 2 comma 0, which is 6 comma 0. In other words, in the standard way, in the old, standard R2, 2 times 3 comma 4 would give me 6 comma 8. But here it's giving me 6 comma 0. Now, what's really interesting about this example is that all of the 10 axioms, 9 out of 10 axioms are going to work, but it's just the very last one that ain't going to work. Because the very last axiom was that I can multiply a vector by 1 and get the same vector. But that's not going to happen here, because 1 times 1 comma 1, according to the definition that we're giving here for scalar multiplication, 1 times 1 comma 1 is going to equal 1 comma 0. And of course 1 comma 0 is not the same as 1 comma 1. So this failed one of the 10, only one and only one of the 10. So it's interesting because nine of them pass and one of them fails, and that's enough to fail the whole thing. But what's more important is to show you that these are vectors that we've seen before, but it's not the same vector space. That's what I'm trying to say, because it's the same set R2 that we've seen before, the plane and the standard operations. But because I changed the operation to non-standard, it's a different vector space. That is so important. Okay, now next, moving on. Oh, that's it. Well, that's it. Yay, we finished 4.2, and we will see you next time when we do 4.3. Everybody, ciao, and it's been wonderful. Bye.